Hi Situndi, how are you?
Hello, sir. Good. What about you?
Good. How? Good week. Finally, we got some rain, so uh, the the temperature is going down, so it's actually quite good. Okay, so can we please do go through the videos? So all the videos are there in my channel, so you can just go through the playlist, and wait, I'll show you how to find it. So in the
So
channel.
I just found it and I watched it.
Okay, perfect. So when you in the channel, I do have my playlists. Are you passionate about here? So all the playlists are there, and that is sorted according to the grade. So when you click on the grade, you can see the full playlist. So all the videos are sorted down, as well as
Yeah.
you can find it on the LMS also. Both it is available on both the locations.
So I watched the recording last time.
Okay, perfect. If you have any questions when you watch it, just let me know. Just send me a message, and I'll be more than happy to reply. I won't. Sometimes I won't immediately reply. I might be in a meeting or in the class, but once I'm free, I
Yeah.
will obviously bring you back. Okay, perfect.
Yes.
So we jump into Unit 4. So we'll be starting from Unit 4 today. So this is a foundation into learning about binary. So don't worry, we are not going to go very in depth into calculations and all, but this is the place where we will put the foundation, where we will learn about the fundamental concepts. Okay, so binary is something you will uh, as long as you are in the IT industry, binary will be there with you, because binary is the way computers talk, right? So you have no choice. You must learn it. Okay, there is no way of skipping it. As well as binary now, when it comes to advanced programming, advanced level programming, we do use binary for, let's say, to make things much run faster. Okay, so there's this thing called binary shifting, and we do different types of calculations based on binary as well. So we'll learn that when we are going forward, but let's see how it works. So last week we discussed about protocols and this the few real world examples about QR codes and how it works. So please refer to the video. It's nothing complex. You can easily understand how it works. Perfect. So Unit 4. Unit 4, we'll be talking about a new point called binary representation. Okay, so we will be going into how computer systems work and how data storages and digital data is being traveled back and forth in the internet and with the networks, as well as we will be talking about how these calculations and how these numbers are captured together. Okay, so in simple terms, binary is the language of computers. Okay, so how it works is, as we know, binary. Oh, we'll just forget about the whole thing about binary. Um, do you guys know how, where computers started? Like how people got into this idea about a computer can make some calculations?
The computer can make some calculation at the first moment they got it by just by an abacus.
Yes, perfect. Great answer. Abacus. And do you know that this whole concept about computers came up to be because of Thomas Alva Edison, the person who invented the light bulb? Okay.
Yes, sir, because he was the one who literally brought electronics and those calculations and those things to the
Correct.
world by inventing the bulb. And when he was inventing the bulb, he needed those things.
Yes, actually, now he got all these calculations done for the electricity transfer, which ultimately ended up glowing and which ended up converting that into a bulb. But what happened was this whole concept behind having a, let's say, something known as the transistor, actually was invented as a byproduct. Okay, so he was trying to build a good bulb, and then ultimately he tried different ways to make sure that the bulb is efficient, as well as the bulb can stay a long time. And apparently, when he was doing this as a byproduct, he found out that when you transfer electricity, when you send the current in different ways, you can create a switch. So ultimately, you can take a switch. So if 2 points are active, 1 point will be either active or on or off. Okay, so that was the initial stage where people got to know about this something known as switches. Okay, ultimately that got converted into a transistor. So I'll show you guys a quick video. Okay, so this is a video about how transistors work. It's just a quick video. So we'll go through this and then we'll jump into binary. So let's see how it. I hope you guys can hear the sound.
Modern computers are revolutionizing our lives, performing tasks unimaginable only decades ago. This was made possible by a long series of innovations. But there's one foundational invention that almost everything else relies upon: the transistor. So what is that? And how does such a device enable all the amazing things computers can do? Well, at their core, all computers are just what the name implies: machines that perform mathematical operations. The earliest computers were manual counting devices like the abacus, while later ones used mechanical parts. What made them computers was having a way to represent numbers and a system for manipulating them. Electronic computers work the same way, but instead of physical arrangements, the numbers are represented by electric voltages. Most such computers use a type of math called Boolean logic that has only two possible values: the logical conditions true and false, denoted by binary digits 1 and 0. They are represented by high and low voltages. Equations are implemented via logic gate circuits that produce an output of 1 or 0 based on whether the inputs satisfy a certain logical statement. These circuits perform three fundamental logical operations: conjunction, disjunction, and negation. The way conjunction works is an AND gate provides a high voltage output only if it receives two high voltage inputs, and the other gates work by similar principles. Circuits can be combined to perform complex operations like addition and subtraction, and computer programs consist of instructions for electronically performing these operations. This kind of system needs a reliable and accurate method for controlling electric current. Early electronic computers like the ENIAC used a device called the vacuum tube. Its early form, the diode, consisted of two electrodes in an evacuated glass container. Applying a voltage to the...
See, so this was all because that guy invented the bulb. Okay, so that was, so when he created the bulb, he accidentally invented this whole thing called the vacuum tube. So how it works is you have a cathode, which is going to be the, just think that that's the part which has the electricity.
Cathode makes it heat up and release electrons. If the anode is at a slightly higher positive potential, the electrons are attracted to it.
So what happens is once the power is given to this will start releasing something known as electrons. Okay, so electrons, we can't see it obviously, but that kind of flies off. Okay, so what happens is when this is turned on, automatically these electrons are sent out, and depending based on the power of this, the number of electrons which is going to be sent off from the bulb. Just think that once you, okay, don't get yourself confused about the word electrons. Just think that it's something like heat. So when you turn on the bulb, it gets heated up, right? So depending on the voltage, the number of or the heat increases, right? Which can be used to control the circuit. In the previous slides in that video, you guys saw that there are these switches which is known as AND, O, and NAND, right? So what they do is they do the same thing, which will make sure that when the power is given, something happens. Okay, some sort of an action happens. So check this out.
Completing the circuit. This unidirectional current flow could be controlled by varying the voltage to the cathode, which makes it release more or less electrons. The next stage was the triode, which uses a third electrode called the grid. This is a wire screen between the cathode and anode through which electrons could pass. Varying its voltage makes it either repel or attract the electrons emitted by the cathode, thus enabling fast current switching. The ability to amplify signals also made the triode crucial for radio and long-distance communication. But despite these advancements, vacuum tubes were unreliable and bulky. With 18,000 triodes, ENIAC was nearly the size of a tennis court. And
that computer was like, so ENIAC was the first machine in the world. So that had the power of performing only one calculation at a time. Okay, one calculation at a time. So example is like if you take a watch, like a normal smart watch, this performs about, let's say, about 500,000-600,000 calculations, close to 1 million calculations per second. Okay, so this whole thing was only able to perform one at a time, right?
And weighed 30 tons. Tubes failed every other day, and in 1 hour, it consumed the amount of electricity used by 15 homes in a day. The solution was the transistor. Instead of electrodes, it uses a semiconductor like silicon, treated with different elements to create an electron-emitting N-type and an electron-absorbing P-type. These are arranged in 3 alternating layers, with a terminal at each: the emitter, the base, and the collector. In this typical NPN transistor, due to certain phenomena at the PN interface, a special region called a PN junction forms between the emitter and base. It only conducts electricity when a voltage exceeding a certain threshold is applied. Otherwise, it remains switched off. In this way, small variations in the input voltage can be used to quickly switch between high and low output currents. The advantage of the transistor lies in its efficiency and compactness.
Okay, so I know that's a bit technical, but then again, so you guys got the basic idea, right? So that concept about switching the power into some direction invented the concept of binary, right? So now
Sir,
yes.
in our computers, sir, are we having those transistors?
Yes, but
Those big ones?
not those big ones, because your CPU contains okay, what is your computer? What's the machine you are using right now?
So I'm using an HP Intel Core i3.
So in your CPU you have 382 million transistors.
He's having like super processing power.
Yeah, so that is in your CPU, right? So ideally, as it says, it's about 382 million to 1.4 billion transistors. 1.4 billion transistors. So in that small block.
That small chip sort of.
Yes, yeah.
It
So
is even so not thick.
yeah, let me. I have a PC here, so let me show you the CPU of this.
So I even asked my mother to bring the old PC to see that Intel Core thing.
Okay, so this is a CPU. This is a small
Wow.
CPU. So this is a CPU. This is this is the size of it, and you can see the back side. So here you can see some circuitry as well, but you can see these are the pins which the CPU is connected to the motherboard, right? Okay,
So,
so
sir, those small things are transistors, right?
no. These are just the pins which will connect this to the motherboard. So these are the pins which will connect this to the motherboard. But inside this casing, you have the main CPU chip, and that chip contains close to 1.4 billion transistors. So there are some videos. Okay, let me show you.
Sir, how could they like pack those things, sir? And how could they even make those transistors?
Those
Are those transistors made by DNS or something?
No, they are actually made by computers. Okay, let me show you one thing. So a CPU under a microscope. Okay.
Sir, I could check it because even I have microscope.
I think in order for you to check this, you need to have a electron microscope. Okay, so check this up.
Okay.
Cool.
This video provides an intriguing look inside a microchip, starting with zoomed-in views captured by a digital SLR camera before transitioning to a scanning electron microscope.
See now this all this area. So this is like inside one of these chips. Huh? So this is by looking into using a electron microscope. See what happens when you zoom in. So see, you can.
So those small things are.
Ideally, yeah. So ideally, those small legs are actually part of those transistors. So you can't from the naked eye you can't see it. Obviously, that's like really small.
So,
So
sir, how could they process those things?
they are actually created
This
based
is
on
a
a different
close-up
process.
look at what it would be like.
Look at this one. So this is actually a close-up look of a CPU and Apple CPU. See, once you zoom in, you can see.
They are super CPUs.
Yeah, they have massive structures in it. See.
They are like mini buildings.
Exactly. See, now once you zoom in only, you can see the circuitry.
That much small.
See? No, it goes on.
It is having like ears.
It goes on.
Wow.
It goes more.
So from those small things, it transfers these all things in around us, right?
Yeah, so it's like this. So just to make a simple calculation. Okay, let me show you another video. I'll share these videos on the chat as well. Okay, there's a video called what's that guy's name? She. Here. This is
or NACA.
Okay, let me show you how it works. See, okay. So this is how the early computers worked. Okay, so you had the circuit like this. Okay, and then when you enter the power, this circuit gets completed, and depending on the circuit, the output changes. Okay, now in the early stages, when you wanted to make a calculation, this is how it worked. Okay, hold on. So let's say if you want to, so you get two inputs, input 1 and input B. So let's say two numbers, and then that's get calculated. So see, if input 1 is added, then output is 1, and if the if there is no input, then it's 0. And again, if input 1 is added, then output becomes 1. Right? If both are added, then you get 2. Right? That's the typical way of calculations are being done. Okay. So check this out. So this was the initial. So what you saw was something similar to this. In the scans, you saw something like this. See? So how it works. So now zoom karahama, you saw some buildings kind of thing. Those are transistors. So that is so the sole purpose of that transistor is to perform this activity. You give current from one end and you get an output on the other end. That's it. But so now this is just to do the calculation of one digit, no? So if you want to do the calculation of 10 digits, then you need 10 transistors, right? Likewise, to play a game, you need like billions of calculations per second. So that means you need billions of transistors. So now,
yeah, so that's why, like, when you have to, like, it is like we are having small bulbs in our screens, no? So they are doing like this by this time, this time, like that.
Exactly.
That's why.
That's right. So that is actually one of the reasons. Okay, since you mentioned that, so if you take a high-end display and a high-end game, and if you try to play it on a slow CPU, let's say an older CPU, the game will not play, right? Or if you try to open a software which requires high CPU power, it will not be able to do that because that transistors are not powerful enough. So it kind of slows down. See, this is what you actually saw in that zoomed in version. So each of these blocks represent one transistor. So now
one transistor represents one mini bulb in this computer.
Something similar to that, exactly. Not exactly, but yes, the idea is similar. Okay. So in this video, we can see this guy has made a old computer, right? So when you want to do a calculation, what you do is you have to select what are the points you want to do. Okay, so let me open the sound and play it.
1 0 is 2.
Yeah.
And 1 1 is 3. And so then when you want to calculate it, you just hit the go button down here.
I love the sound of that. That was amazing.
It's magical. So if you want to do, like, say 8 plus, that would be 4. So 8 plus 8, I think, right?
Okay. So in binary 8 is 1 0 0 0. Right? We'll go through this later on. Don't get confused about the numbers. So there's a way you write binary numbers. So now, since it's on and off switches, that means you have to give the command in binary, right? So here, what they do is, this is a switch panel. So this is basically a calculator. So what you do is you just calculate two numbers. So you provide the binary representation of 8, which is 1 0 0 0, and again you provide 1 0 0 0. So what it does is it checks the two values, and
okay.
Yeah, 8 plus 8 would be 16. No, it clears it on its own.
Okay.
There you go.
And you get 16 as the answer.
8 plus 8 is 16 in binary, which
16
would be
in binary,
1
which
0
is
0
1
0
0 0 0 0. Okay, so you're on mute.
So sir, how could we like tell? How could that thing tell? We are asking it to do an addition or multiplication or a subtraction.
That is again depending on the different paths. So this is just to add numbers. So if you want to subtract it, then the circuitry has to be changed. So just by now, like example is just think now, you just take your calculator and you press 2 plus 2. Instantly it gives you the answer, but see how much processing things happens behind the scenes. Check this out. So
this is essentially a 1-bit arithmetic unit. There's no logic functions. It only ever does add. Now let's say we want to do...
So this only does add. So you don't have any other arithmetic operations in it.
5 minus 2. The answer is going to be 3. So we flip this little switch here that lets me know that I'm doing a subtraction operation.
Subtraction.
And we do subtraction by doing 2's complement. So essentially what we're doing is we're inverting one of the operands and we're adding 1. So now when I run it, we can see 5 minus 2 is equal to 3. So 2 and 1 is 3.
Okay, so that's the... Oh, yeah, okay. So that's the whole concept behind computers and how things work. So now here, these guys press this by using buttons, no? But when you go back, ENIAC. So ENIAC was something like this. So
it only had a little display for only for like huge tags or something.
Yeah, no displays.
Programmed.
We didn't have displays back then. So literally, this ENIAC had, now here this guy had switches, no? Back then we did not had switches. What we had was wires. Okay, so we had trained people who had a big paper of conditions, what needs to be calculated. Okay, then what they did was they manually go into this point and they flipped all the switches. That is to make one calculation, na? One calculation. See how much time it takes for them to see. They are switching all the knobs, turning all the knobs, making sure that it's correct. See that woman has a paper with her. So what she does is she goes through the paper and she turns on or off all the switches. And then after that is prepared, then they run the computer, which will run the calculations.
So sir, that means can it do like huge calculations or like can it only do like 1 plus 1?
No, like massive calculations. So you can basically program it to run like a scenario, something like a set of calculations, and it will run it like that.
Oh, really? But so those same calculations can be done in a normal phone these days, right?
Not in a normal phone. Like, what do you think?
In children's those things.
You have those small toys where you play around it. Those have microcontrollers and microchips. Even this.
Sir, even in our brothers, he had a toy called a cashier, one sort of thing.
Okay.
And he can actually calculate with a display.
Exactly. Yes. Yeah. But this thing was actually inside a huge building, and they say when the computer starts doing calculations, the entire city got a power surge, and most of the parts of the city went down because this is taking too much power to make a calculation. Now our phones last for about 2 days now, with all the displays and all. Okay.
Yeah, sir.
Super. So that is where we started off. Now that is where the whole concept behind binary came up to be as well. Okay. Now you guys know the history, because without knowing the history, it's not interesting. Now you know how interesting binary is, right? Okay. So I want you to highlight one point. So this is a common question which you are going to get. What is binary? So binary is the language of computers. Okay. So you can either write it down, or since if you have the book, you can highlight it as well. So just make sure that term is highlighted, right? Okay. So then the next point is the one I just showed you. So the central processing unit, the CPU, of every computer, as we know, that is the brain, and this particular brain contains billions of transistors, which that can be either on or off. Right? So by using this combination of on and off, then the computers can be computers can be programmed to process a certain set of actions. Right? So binary can be converted into multiple different points. So it can be either converted into text, and numbers, as well as graphics and sound. Okay, so in simple terms, here we are actually not going to go very in depth about the binary calculations as much, but we do write some things. Okay, so first of all, let's see how these images are made of binary. So now, images. Okay, so technically an image is okay, think about this in a different way now. If you take a screen, your screen is created based on small bulbs, right? Small pixels in this case. So now we have LED displays, LCD displays, IPS displays, and so on and so forth. Everything works in a similar way, where you have a small bulb which will be illuminated by using electricity, and this particular bulb will have different abilities to show content, right? So now this output, the images and the details which is going to be displayed there, is created using binary representations. Okay, so now if you take this example here, you can see that this particular block is actually like a single bit display, right? So here you have either black or white. Okay, only two colors are there. So that means when it comes to the binary representation, you can see black is 1 and 0 is white, empty, right? Either you have the data or you don't have the data. That's it. No? So by having a panel like this, 0, 1, 1 and 1, 1's in the side, you are able to create a graphic like this. Okay. So this is how the typical binary drawings are being created. So you can see another example here. So in this case, we can see that we have all ones and zeros, and that allows you to draw this particular image. Okay. So that's how. So that's a simple example, because this is using a one bit binary graphic. 1 bit. So what happened was, back in the day when we started, when people invented computers, we did not have the capacity to process high number of bits. So that's why all the games looks like this, are block games.
All the games looks like sort of squarish.
Exactly. Because the thing is, okay, so to make a character to make a high definition character, you need a lot of blocks, right? So one block, if one block means 1 bit, that means you need to have at least about couple of thousand bits to process that character, right? The problem is, we didn't have couple of thousand bits back in the day, because our CPUs were very limited to a limited number of transistors. So when we don't have the transistors, that means we don't have the capacity to process. So we were limited with that graphics. So same thing happened for sound also. The sound, we will go to the sound in a while. But in the old days, you had very different types of tang 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 tang. You don't have the nice way, what do you call it? Nice rhythmic sound. It's all teets.
So it always had not the sounds are so not in a streamline or something. It is always having a that means a beat. It's
Exactly.
having a beat,
It's just beats.
but not a waves. That's the problem. It's a tut 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 or something.
Exactly.
And sir,
Correct.
when we like, sir, if you know, sir, there's a game sir, that is like sort of block tree,
Okay.
and it was in old days night. Sir, do you know that Mario jump and those
Yes,
things?
yes,
That
yes.
Mario jump, that thing is still like in square type.
Yes, yeah. So I think now, okay. So if you go very long back where we had the Game Boys, so the Game Boy is actually one of the best gaming handheld gaming devices which we had back in the day. So that entire display was created using dots, and then the the character was literally drawn using dots. That's how it worked. Let me
Oh,
show you a
those
quick
days.
game. This is one of my favorite games.
Game Boy.
Game Boy, Game Boy Batman.
Oh, those things, sir. Those things are black and white most
Yeah,
probably.
yeah, yeah, yeah. I
And sir, now even sir, these days sir, we are having those. Even I have sir those small screen, and
okay.
it is so affordable, sir. Even our father bought it, sir, and it is totally made like blocks.
Is it okay?
It's similar for Game Boy.
I had one of these.
Those.
Yeah.
That's nice.
I have one of these, but it was long time ago. Let me show you a game how it looked like. Cool.
Sir, but I like those that not also not or something. They had a high pixel sort of a port, but it's
Yeah.
specially designed to play games.
See, this was the
Batman.
this was the Batman game back then. See the graphics. So it's all created using dots.
So what is that TMP?
TM is trademark.
Oh,
See, you can see the
that is
dots.
interesting. Yeah, those things are so small. But
Yes.
so they should have like high processing area, so all sort of
Yeah,
process it.
but not that high because the screen size is very small, no. So the number of pixels you need to process is really less. But this was long time ago. I had this back in I had this back in now late 90s while I was in grade 4 or 5.
So nowadays we should have not those that thing made by that Mario company or something.
Nintendo.
That game one is sort of like a phone.
Yeah, Nintendo. So that is
Yeah,
so
that
this is how it worked. Okay, so I just wanted to show you how this how the pixels are like. So depending on the CPU power, that was limited. Now we have like high-end CPUs and high-end GPUs. So that's why now we are into more realistic games and realistic
the gaming
engines.
computers.
Yeah, gaming computers. Plus nowadays, now we actually have a whole different, let's say, whole different type of computers dedicated for gaming. No? Back then, the computer was actually used to do office work, not to game. But now only they have like come up with a actual purpose called gaming. Plus,
Sir,
yeah,
even so now we can like measure the graphics and those things by FPS, frames per
exactly,
second.
frames per second, exactly.
Sir, I
Exactly.
have 80 frames per second.
80.
When I'm yeah,
What is it?
80.
What are you playing on 80?
Sir, once when I was allowed to play games, I played the block style game, sort of like Minecraft.
Okay.
And so it showed you are having 80 FPS.
Yes, yeah. I do. So normally,
And so it was super fast, sir.
yes, exactly.
Because in those I got like in survival and those,
Uh,
I could like quickly mine and those things
yes,
because
yes.
of that.
Exactly. So whatever the frame rate if it is more than 30 frames per second, that's perfectly fine. You won't see any let's say any lags in the game.
So
That's the
our
limit.
father is having the highest one.
Okay. So jumping back to this. Now, since we saw how the pixels was created, so this is how the binary sequence is saved. So it's quite straightforward. If you take a look at this, you can see it's 1001. So what you do is you take all the lines starting from left to right, and you can write it as a sequence. Okay. So now this particular sequence is the one which is going to be saved and which is going to actually process in the system. So to draw something like a graphic like this, you keep a binary sequence similar to this one. Okay. So going down, we'll see how it actually works. Okay. Now we have a concept called binary value tables. Okay. So this is something which you guys will have to write down and understand, but we will actually learn more about this once we go to in the coming pages, where we will be talking about binary calculations. Okay. Now how this works is, now for the moment we are only going to talk about 4 bits. Okay. 4 bit means this is known as a single bit. So what we saw here, so this is a single bit. Okay. It's either 1 or 0. Okay. So now here if we take 4 bits, okay, 4 bits means that is going to be equal to the power of 2. Okay. So it's basically like, so if you take 1, so this is 1, 2, 4 and 8. Okay. So those are the representation of these 4 bits. Now when you want to convert a value into binary, what we do is we just need to make sure that we can put this under this particular set of 4 bits. Okay. So now let's just take a look at this example. So if you take the binary number 1, that means in this case binary ones, it should be 1 on the first, right? Otherwise it's all zeros. And then if we take number 2, then that means here, so 2 means it's 0 and 1, because the first 2 zeros are 8s and 4s. So the third 0 is 2 and the fourth one is obviously that is 1, right? So if we do this, like if you write it like this, number 2 means it's 1 and 0. And then again if you go to number 3, it's going to be 1, 1, right? Likewise, when we go with 4 bits, okay, so when we go with 4 bits, we can go up to how many numbers? We can go up to 16, right? So we start from 0 and we can go up to 16 based on these numbers. Okay. So binary is not actually hard. You just need to keep in mind how you make these calculations. So the first one is 0, second one is, sorry, the first one is 1, second one is 2, 4, 8, and likewise the binary representation goes on forward. So 2, 4, 8, 16, 32, 64, 128, 256 and 512, and it continues. Okay. So that is how the binary number range gets converted into denary. Denary is basically decimal numbers, right? Okay. So let's see if you want to convert a number. So let's say if you get the binary number 1011, okay. So how do you convert it? You basically, now you you know this is 1, 2 and 4 and 8, no? So 1, 0, 1, 1 means, technically speaking, since we have 1 here, that means that is going to be 8. Since we have a 0 here, it's going to be 0. Since we have another 1 here, that is going to be 2, and another 1 here, that is going to be 1. Right? So altogether, so the calculation is then 11.
So that means if we are having a 1, it's 8, and again when we are having 1, it's 2?
No. Okay, so it's like this, no? So okay, let's take a number of maker. So you guys can, I'll put something. So let's take a number and let's write it down. Okay, so let's say 1100. Okay, so if we take this number, what is the representation of this in denary? In denary means how do we convert this into what do you call it? Normal decimal numbers. Make equal and kiyatද?
Sir, we are just putting the 2 to the powers and going by like that.
Exactly.
Like 2 to the power 0, 2 to
Yeah.
the power 1.
So first one is, so here just by looking at it, so since we are looking at only 4 bits, that means it's 8, 4, 2 and 1, right? So in this case we have, what do we have? We have 1, 8, right? 1, 8, and the second one is 1, 4, right? And the third and fourth, it's all zeros, right? So what's the answer?
The answer is 8, 8, 4, 6,
8,
no,
4.
8 and 4, 12.
Yes, the answer is 12. Correct, yes. Okay, so let's try another one. Let's try this one, 1, 1, 1, 0. How does this will work out?
1, 0, it's 14.
14, correct. Exactly. Okay. But we'll do another one. Now, what about, let's take something like this. So 0, 0, 1, 0, 0. What about this?
0, 1, 4.
Exactly, that is 4. Perfect. Okay. So
Thank you, sir.
yeah, let's do one more. Siddhamdi, can you answer this one? What is 1, 0, 1, 0? Yeah.
Sir, could you teach that part again? I don't understand.
Perfect. No problem. Okay.
So the answer is 10.
Yes, the answer is 10. Yes. Perfect. No problem. So, Siddhamdi, this is how it works. So now we have, so here we have four binary goes as bits, no? Bits, right? So if it is 1 bit, that means you can only have 2 values, that is either 1 or 0. Okay, that part is clear now, honey? Okay, perfect. So then when you have 2 bits, okay, so if you have 2 bits, what would be the combination? So let's say if it is just 1 bit, okay, 1 bit means 1 number, right? So it can be either 1 or 0. But if you have 2 bits, then this changes. So let's say if we have 2 bits, this would be, so 0, 0 is 0, no? Then 0, 1 would represent technically 1, right? Because according to the 2 to the power complex, like how we go forward, 0, 1 would be 1, and 1, 0, what is 1, 0 then? What would be 1, 0? Yes. Siddhant, did you get the point? So in this case, if you take it as 1, 0, that means, like, look at this part. So here, this is the table. So if you have 2 bits, that means the maximum you can go is 1 and 2. That means you can go up to 3. Right? So here, if you take the number 0, that is 0, 0. And if you take number 1, 0, 1. And the second one, if it is 1, 0, then that means it's 2. And then if we go as both 1, 1, then that means the answer is 3. So that's how the binary representation works. And now here, what happened? Now, since when we have only 2 bits, this is the maximum we can go, right? We can't have any more representations. If it is 2 bits, it's 0, 0, 0, 1, 1, 0 and 1, 1. But if we add another bit in front, then what happens? This gets multiplied by, again, 2. So now if we add another bit like this, if we go with something like, this, then that's going to be another bit which will then represent 4, right? 4, and as you guys can see in the table, it will then go up to 8. So 3 means it can go up to 8. Okay, and if we add, it can go up to 7, like 0 to 7. And then if we add 4 bits, then automatically that can go up to 8, which will then, from 8, that gets doubled, because then it can go up to, it will start from 8 and it can go up to 16. Got the idea? Siddhant, how is it? Is it clear or?
Yes, now I understand it.
Okay, let's try out a question. So, what do you think this is? 1Z. Yeah. What about if you take 101, what would be the representation? Oh, sorry. Okay, 1 second. Yeah, sorry. What would this be?
I just sent the answer.
Yeah, don't send the answer. I'm waiting for Siddhant to answer.
No, I sent the answer for sir as a directed message.
Okay.
So is it 2?
Is it 2? No. Now, since we have 3. Sorry. Yeah, so make a bindu of missing banana. Yes, this is 2. Yes, correct. Sorry, okay. No, I was going to add another 0. Okay, what is this one? Exactly, correct, perfect. So, how did we make the calculation? So, we have 1, 1 and 2 is 0. Then we have 4. So, 4 we have 1, 4 and 1, 1. So, that means altogether it is 5, right? So, if we go into a little bit of a complex one, so let's say if we do something like this, then what would be the answer? 13, exactly. So, how did you make the calculation? So, this is 1, 8, 1, 4 and 1, 1. So, 8 plus 4, 12, 12 plus 1 is 13. Okay. So, that is, so these 4 bits are actually quite easy, right? It's easy to calculate so that you can come up with the number of points down the line, which will then give you a clear view about how to go forward. Right? So we'll jump into few calculations later on. Hold on, just remove this, and so this is how. Okay, so now when it comes to the computer, the way the computer understands things, so whatever the actions we perform, all these actions are technically converted into binary. Now what we did here was we got it in a way where we multiplied it, we got it into the 2 to the power complex, and we managed to convert it back to binary, right? Other way around, we will have to, but later on we will get questions, and points where we will discuss how these can be converted back and forth, and at the same time there are binary calculations also, where we talk about how systems can be, how two numbers can be calculated. Same thing like as you just saw in that video. So where you get the two numbers together, and these two numbers will be calculated to get the final value, right? Okay, so guys, can you write down this particular table? Why you really need to, because this will basically make sure that you practice it. So get the binary values. So technically you get write down this up to, don't write the full thing. So write a 3-bit table, 1, 2, 3, 3-bit table. So it should be starting from, then what? It would be starting from 0, 0, 0, right? So always you have to read it from right to left, not left to right. So when you are writing it even, so you just write to 0, 0, 0 and 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 0, 0, 0, 1, 0, 1, 1, 0 and 1, 1, 1. So altogether you will get 8 points. So the idea would be 7. Okay. Can you write it down? Just only that part?
Okay.
Yeah.
Okay, sir.
Yeah, perfect. Sidhunti, please do write it down as well. Yes.
Sir, 3-bit, right? So, sir, we should write only 4, 2, and 1, right?
Yes,
For 3-bit.
exactly. Correct. But you got the idea, right?
Yes, sir. So, up to 16, no? Up to 10, no?
Just copy the same thing. Go up to 16. Sidhunti, can you do the same?
Okay,
Yeah.
sir, could you move that table a little high because I can't see the
Okay.
text.
Let me increase the size then. Hold on.
Now can see, sir.
Oh, hold on. Na. What happened? Okay. Sorry. I increased the whole font size. Okay, sorry, my bad. Let me zoom it in. Nice. Okay. Now you can see the top part. So I want you to complete this.
Excuse me, sir.
Yes, shoot.
Sir, are we having, sir, any paper classes these days, sir? Because we are having the exams, sir, in March 20, around 20.
Okay. So that day you told me that we will be
Sir, we have done up to only binary representations in school, sir. So,
I
sir,
said.
yeah, sir, as I think we did sort of programming too. And sir, after that, sir, the programming, those programs and these will only come, sir, for this term's exams, sir. As after completing those, can we have a paper class, sir?
Yeah, obviously, yes. So you will be getting your exams by end of next month, right? Somewhere.
Yes, sir.
Somewhere by okay. So what is the have you done a lot into programming or
No, sir, only those like scratch and those we had those some commands, only scratch and those some commands that they have given in the book.
got it? Yeah,
And sir, I'll ask to be sure, sir. I'll just ask from the teacher, sir.
got it. Yeah.
I'm going to school next week, sir. So
Okay.
I'll ask from the teacher. Then I'll tell sir which programs and which programming lessons we can do.
Sure thing. No problem.
Sir, most probably they did Python, but sir, in these things they are showing sort of HTML also.
HTML. Okay,
Yeah,
but
sir, how they are showing another thing.
which module are you looking at?
Sir, in Python, in the last one, sir, they are telling Python programming, sir.
Yeah.
They are not doing like the same as Python. They are doing something else.
Okay. Kemit, what is the unit you are looking at? Which unit?
Sir, I'm looking at the unit 5, sir.
Unit 5. Yeah. Okay. Yes. Okay, so you completed up to unit 5 at school.
Yes, sort of. And into like, I have to ask it correctly, sir. I'll let you know, sir. Like, I think they went to unit 6 programming.
Okay. But for the exam, are you certain that you are going to get programming questions as well? Because that would be a written exam mostly, right?
Yeah, sir. I'll ask and I'll tell, sir.
Yeah. Okay. We'll just jump through as fast as possible. So this binary part, did you cover it at school? Is it all good?
Yes, sir. We covered it at school. But I'm mostly sure, sir, binary and these parts are coming, but not unit 5, sir, much.
That's true. Yeah, because I'm not sure that most
Yeah,
probably
sir.
you won't get programming.
Sir, I'm even not sure we will do programming because even in schools, sir, we use Linux.
Linux, that's good, no? That's good.
That is good, sir. It's like in our school, like in our school computers, sir, they are like, sir, nothing, sir. We doesn't have Google Chrome. We only can go like those. And even one of our guy had even Intel Core 98 or something. That all.
Okay. Yeah,
And
but
sir, like
having
other new
Linux is actually good.
is making. And sir, our teachers told that now you would get new Intel Core computers, but those are still they put the old computers in the old IT lab.
Schools actually they don't prioritize that much of on computer hardware because you don't need supercomputers to teach.
Sir, if they know about the England schools, they should give us IMAX. Because in England they
Yeah.
even pay their children Minecraft accounts and give
Yes.
them in the IT school.
I know, yeah, that's true. So I have one of my friends living in Canada, and what he told me was there are schools, like when a new CPU or Intel CPU is released, apparently the school changes all the computers. So every 5 years, the school literally throws out all the existing computers and buys out new ones. But then again, they have money, so.
Sir, I have a question to ask, sir.
Should,
Sir,
yes.
I had a laptop, sir. It is an Intel Core i2 computer. And
Core
sir,
i2 computers
i2,
should be
i2,
Core
sir.
i3.
i3, yeah, sort of i3 or something, sir. However, sir, it's part, sir, that I told the scene that my Arduino set was that my Arduino program went wrong, and with the adapter plugging into the normal current, and the Arduino board is plugged into the laptop. And I was like programming the servo motor to like turn it in these angles in a voice controller,
Okay.
and it sparked automatically when I switched on the program and in the morning. And I forgot to shut down the computer last night, and it sparked. And the people who was going to make it told that the laptop's motherboard had sparked. So,
Okay.
if I bring the laptop to home, like what had happened to it?
Uh, when it comes to when it comes to USBs, usually if your circuit board had some sort of a short in it, there is a chance for the power to go back into the motherboard. So if the servo got something burnt, or if you have like used the wrong pins. So okay, so in you're using a Arduino board, right?
Yes, I used. So,
Okay.
can't I make it at home?
You mean to fix the laptop at home?
Yes, that means I can take others' help.
Yeah,
Like,
but then
what is the thing I had to replace? What was
usually if it is a power surge, usually right, okay, so normally what
yeah.
happens is there's a thing called a USB controller. So the USB controller can get burned. If that's the case, you can't technically we cannot repair it at home because we don't have the required things to do that, because usually if you are going to replace a chip, you need to have a hot air gun and you need to find the exact controller chip. That's the thing. So first of all, you will need a good multimeter to check the motherboard. Plus, you need to get the schematics. You will have to find the schematics of that motherboard to pinpoint and find which chip has been burnt. But there are people in Sri Lanka who does that type of repairs. Not the big
Sir,
companies.
the
There are.
problem is our mother told but I'm sort of like this guy, I don't like to do those things. Our mother told that they even gave it to the Haymax or something, and those guys even told we can't make this, but I'm still sure that I can make them.
If we can find out what is exactly or which ship exactly has been burned, then that can be replaced, that can be easily replaced. But the challenge is with that finding out part. So you need to find the schematics. Schematic means schematic එකක් කියන්නේ motherboard එකේ layout එක. So you can find the layout of that circuit board, and then from the layout itself you can find out what is wrong and check out what can be replaced.
So if I have those multimeters in the
Yeah.
factory, in our factory, I'll tell our father to bring the multimeter. So like I last that day when it's brought like how to put the multimeter in the each chip. I
That,
know how to measure those things,
okay.
but in each chip there can
Exactly.
be a
Yes.
variable
Yeah.
label.
Yes. That is why I highly urge you to find the motherboard schematic first. So in the schematic diagram, it actually shows you exactly which chip is there and the power ICs and how the voltages goes on and so forth. Okay, is it done? Shall I jump to the next part?
So
Four
I'm
bits.
now calculating and writing this.
Okay, Siddhamdi, were you able to complete it as well?
Yes, I completed it.
Okay, did you write up to 15?
Yes, sir.
Perfect, all good. Yeah, Kevin, can you finish it up soon?
Okay.
I'll give you 2-3 minutes.
Done.
Okay. So, yep. So, yeah, so let's jump back to this one. So binary computing. So, I actually started the lecture with going through this where I explained about this concept about the bulbs, right? So, as we saw, all computers have these transistors in it. Okay, so now can please do highlight this part. So you do get questions asking what is a transistor. So a transistor is a type of switch that controls the flow of electricity in an electrical circuit, switching it on or off. Okay, so if you get the question, or when you get the question, this answer is more than suffice. So a transistor is a type of switch that controls the flow of electricity in an electrical circuit, switching it on or off. Okay, so now in the example we saw in this 8 by 8 small graphic, so basically to produce it you need to have a certain set of switches, right? So in order to give that output, that binary process has to be switched, right? And then only that is going to get sent out. So example is, so here we have another real world example. So in 1954, the first transistor based computer, so Tradic is actually a computer which was invented before ENIAC. So this actually contained around 700 transistors. Okay, but now the new Apple M1 processors, they contained close to up to 16 billion transistors. Okay, 16 billion, and I think this one of these phones, and iPhone, these contains more than that, because they have like multiple processors to process multiple activities, like to check the sensors, to control the camera, to process AI, and so on and so forth. Okay, so transistor. Yes.
M1 chip is more powerful than Intel Core i3, right?
M1 is actually okay, so I won't say it's more powerful. It is a similar competitor. So the thing is, the Intel and the Apple M series processors, they do work using two different CPU architectures. We don't have that in your syllabus, but you just check for that when you get a chance. So there are two different types of architectures called ARM. So M series CPUs works based on this architecture called ARM. Okay, so the ARM architecture processes, let's say, processes data or information in a bit of a different way, but it has pros and cons. So this it's called CISC and RISC. So ARM works in a architecture called RISC, and Intel works in a architecture called CISC. So how it works is the ARM CPUs. Let's say okay, I'll give you an example for this. So think about think something like this. So you have two. Okay, go to if you go to Keels or Cargills, you have multiple checkout counters, right? So think about this in a way where Intel is similar to Keels, where you have multiple checkout counters. So if you have many people walking in, you can send them to different counters. But ARM or the M series RISC works in a different way, where you have a single counter, but that counter is fast. And just think that counter has a security guard in front, and he looks for urgent or people who really wants to go faster and get them in first. So got the idea? So it's
sir, the most like urgent and that means most important those
important
things.
first goes first. And the thing is, now Intel, that is why Intel and all, they are like more efficient in gaming, because for games and high performance applications you need lot of CPUs and lot of threads. In this case, so if you need multiple threads, then Intel architecture will give that to you. But ARM works in a different way, where you work on one thread at a time. But the
So
thing is,
that's why sir, in most offices they
Yeah.
use iMacs, but in gaming computers they use Intel Core i9, i7
Yes.
and those things.
Exactly. So for productivity and for programming and all, M1s are perfect. So I'm also using a M1 Pro. I actually got this when it was released. At that time, I have a M1 Pro and a laptop which is M2. So now recently they released the M4 laptops. M4 is
Those are
almost.
expensive.
Those are expensive, but this one also I got it when it was released, so this is also expensive. But the thing is, it has a long lifetime. So I still have my old iMac, which I purchased back in 2013, and it still works.
Sir, when I was born, I born in 2013.
Okay, that iMac still works. I'll send you guys a picture on WhatsApp. It still works perfectly. So that's the thing. So even if you spend
Durability.
a bit more money, it will last for a long time. Intel machines,
No, sir,
it's
please.
good that it will last for more than like 3-4 years.
But sir, in the first day, in the first brand new days, sir, these are like super machines.
Yes, that's true. That's true. That's true. But then again, you can't game on Mac. So technically, that's you now you can. Now actually, these game manufacturers are changing the way it works. So now these are getting the support. But back in the day, no gaming, not so much. Okay, I I have a full gaming setup at home. I have a 120 hertz gaming monitor plus all the gaming gear.
I even got that, sir, for like when I asked them, it was like it was having no high, it cost extra. They call like it cost extra because of its mouse speed, and
Okay.
it's actually speed, sir.
Yes,
While we are
yes.
moving the mouse, it's like I can move the mouse so speed, and my friends are like telling, how could you move your mouse that speed?
Yes, yes, that's true. That's true. That's true. Gaming gear has that support. Okay, perfect. Okay, so now we know about the transistors, and we learn a little bit about sound. Okay, so as we discussed before that in the old days we had very sharp sounds, which is also known as MIDI, MIDI sounds. So how it works is, now when you want to convert audio into binary, it works in a specific algorithm. Okay, so this is how it works. When it comes to sound waves, okay, we have something called the amplitude. Okay, so the amplitude is the, let's say, just think about this as the size of the wave. Okay, so you have different sizes of the waves, right? When I speak, you can see the sound goes like this, right? So this size of the waves plus the time duration. Okay, so that's how wavelengths are created. So when you look at this as a graph, now you can see this can be easily represented into a binary format, something like this. So if it is the 0th point, so we have the 0 0, time is 0, amplitude is 0, then obviously the amplitude in binary would be 0. If the time is 1 and the amplitude is 2, here this is amplitude in binary will be 2. Okay, so literally the amplitude points, may points 2, 2, 4, 5, see, these are the points. So these points, what you do is you convert them into binary. So technically the amplitude points are actually taken as in binary, and that is getting represented into binary. So this is how the sound is saved into binary form. So this will basically do the conversion, and when this conversion happens, then ultimately you end up with a certain set of binary values, and you save that into your computer. So this particular binary representation will be saved using some sort of a format. Then we have wave, MP3 and different formats of audio. Okay, so that's how it's getting saved. So this sampling rate and the number of samples per second, that is where the sound quality differs. Now example is, I am using a 24-bit microphone. So this particular microphone, this is actually a studio level mic. So because of that reason, this can convert more data. So that means this amplitude, the data set would be much denser. Okay, so you will have lot of, now here in this case we just have a few set of data points, no? But when it comes to these type of microphones, just think press karna. So if we have a long gap, that means the data is less, right? So if you have a shorter gap, then the data is more. So what these guys does is they capture it with the density so that it has shorter gaps, so the quality is high. I'm just explaining it in a very simple way. Yeah? So that's the idea behind this thing. So that's why these microphones are very efficient and at the same time expensive as well. You have these podcast microphones where they mount it on tables and all. Those microphones are really expensive. No? Like one microphone will cost you more than couple of 100,000 rupees. So
that is a DJI microphone, right?
This is a DJI mic, correct? Yeah.
Those clicking those things, right?
Yes, yeah. I actually wanted to buy a big mic, but then I did a in-depth comparison between the microphones, and what I found out was DJI. So this mic is almost similar to having a big table-mounted microphone. The only thing is the battery life is not that long. So this
those are like easy.
This is easy. You just get it, clip it on, and that's it. The thing is, the battery life, one device will last you for about 3 hours, maximum 2.5 to 3 hours, and then you have to charge it, but it charges really fast. Okay, now we jump into a bit of a hard part. Okay, now earlier we learned how to convert the numbers from binary to denary, which was actually quite easy, right? But now we go to the point where we talk about converting the values from denary means decimal numbers, to binary. Okay, so in technical wise it's the same method what we did earlier, but here in this case we have to find a way on how to split this value, right? So if you look at this one, so binary is using base 2, and denary, the decimal numbers we know starting from 0 to 9, is using base 10, right? So that's the typical theory behind the whole number conversion, right? So both uses something known as a place value to show each digits in number. So let's see how it works. So let's say if the value is, consider the value 125. Let's see how it's going to be displayed, right? So 125 means, in this case, we need to go up to what extent? How many bits are here?
Sir, there is one.
It's up to 6.
7.
7 bits, exactly, right? Okay, so now in this case, in order for us to show this, to show the number 125, that means we need to go up to 64, right? So that means we have 164, 132, 116, 18, 14, and 11, right? So that is how the number representation is done. But when it comes to denary, the place value is actually quite straightforward. So here in this case, 125 means you have, from the base value you have 5, and from tens we have 2 tens and 1 hundreds. So other way around, if we read it, we have 100, 2 tens and 1 fives. So that would convert it
5
into
units, 2 tens, 100.
100s, exactly. So that would convert it into 125, right? So the way we convert this is quite
Excuse me, sir.
Yes, shoot.
Sir, why can't we take them straight away and binary coding panel in our computer?
We can, but can you code in binary?
Sort of.
No way, you can't build a big application in binary. That's technically, that's like practically impossible to do that. That's why we use like programming languages, which will basically remove that particular portion of complexity and allow us to use simple English.
Yeah.
Otherwise, if you know how to code in binary means like, forget about binary, learn how to code in assembly language, then that would be the best. Assembly means technically the final language, like the final coding part which will get compiled. So if you know how to write in assembly, then that's going to be a real high level programming level. But then again, assembly, it's not easy to learn, but if you learn it, then you're going to be a very high-end computer wheels.
Sir, I am learning that Python
Yeah.
nowadays by the DP Education IT campus. You
Ah,
can
nice.
just sign up here. You can learn. And
Yeah.
I saw assembly and I thought assembly, it seems like name useless. Now I'll also learn it too.
Assembly is not useless, මෙහෙමයි. Now, with normal programming languages like Python and all these high-level programming languages, we call them high-level programming
And low
languages.
level.
High level and low level. So high-level languages are the ones we use to build solutions, because now it's like this. Now today I actually build a solution for one of our customers where I coded it. So I created a portal where people can actually subscribe and purchase a ticket. So once they purchase the ticket, there are some specific validations which goes through, and ultimately the payment is handled through a payment gateway. And once you purchase it, you get a gift pack delivered to your house. So I started coding it around 10 o'clock in the morning, and I finished it around 3 o'clock. So that was because I use high-level languages, and because we have server-side processing and different applications to do, we always follow high-level languages. But if I try to do that in assembly, ammo, masa ganak kaya ek liye lega. That's not
So
good.
is it taking like 3 language?
Yeah.
So much coding for a small thing, or like is it taking small codes for like a big thing?
No, it's like a lot of small codes to do a single task. Example, okay, so simply, so I coded it using PHP, the language known as PHP. So in PHP, you have all the components inbuilt. So you have the database connectors, you have the file uploaders, you have the processing part, validations. When it comes to web applications, we have this thing called requests. So how to handle requests. So request validations, handling the requests, and all sorts of things, it is already there implemented in that language. So in PHP, that comes inbuilt. So if I try to develop this with assembly, then I have to manually handle all those points. You got the idea?
Then it's not something practical.
It's not practical. Exactly. So like even the database connection, I will literally have, so in PHP to connect to a database, you need to write is all about 4 lines. So after writing 4 lines, you can connect to a database. In assembly, you will have to write like about 1500 lines to at least to initialize the connection. So because of that reason, we don't use assembly in our day-to-day coding, because end of the day we are focusing on giving solutions. So customer wanted a solution, he paid, so we developed it. That's it. But
But when we are doing those high-end hacking and those things, we need assembly.
yes, and hardware. Hardware works on assembly. So technically, if you are programming something like one of these hard disks, so this is a hard disk. So if you are programming one of the applications to one of these chips, here what you can see.
Yeah.
Then
So how
obviously-
much is it storage?
This is an old hard disk. This is a very old one. I'm just keeping it just to show you guys. Hitachi one, yes. Check the date.
2010. No way.
It's a very old one. It was from one of my old computers.
So that is like 2010. No, sir. I had a separate hard disk, and if you come to our old house, it's in there. So always in that always those computer parts are all the way. And when I was little, I didn't had an idea of sir. I was just playing for nothing. Now I understand what's the value.
Yes, yeah. Okay, so just play around with it. You can learn a lot. Okay, so super. So we talked about the binary and the denary calculation. So like the place values on how it works. So let's just jump in and see how conversions using an 8-bit binary table works. So similar to what we just wrote down, we went until only 16, no? But here, if you take a look at an 8-bit table, here you can see when it comes to 8 bits, you go up to 128 decimal numbers, right? Binary numbers. And so see how it works when it comes to the addition part, the calculation, it's the same way, but here you can understand. Now, since we convert them, so 8 bits will technically go up to the binary numbers of 255, right? So this 255 is actually a big number when it comes to IT, because most of the storages and patterns and everything is actually created using this 8-bit architecture. So almost numbers and IP addresses, validation systems, storage.
Sir,
Yes.
when we are, sir, in Python, sir, it's showing 64-bit.
64-bit for what?
Don't know idea, sir, but it shows like 64-bit Python or something.
That's
Sir,
okay. Yes. Okay.
that shows that means is it having 64 bits?
Yeah, it is actually something known as a. So we had so back in the day when we had computers, like we started using computers, we got different eras. So we had 8-bit computing, we had 16-bit computing, and this in late 90s when Windows XP and all came out, they were focused on a platform called 32-bit computing. So everything was 32 bits, and then in 2000 with the new Windows version, Windows XP, Windows 2000, Windows Vista, we were introduced into 64-bit computing. Now everything runs on 64 bits. So all applications, everything runs on 64 bits, but Python and all still, they do support 32-bit computing as well. But the thing is,
yeah, sir, they do have 32 bits.
Yes, because why?
One of my cousins still use 32 bits.
Why do they use it? Can you
Sir,
think
because
about
he
why?
started it earlier.
Not exactly. 32-bit use කරන්න වෙන හේතුවක් තියෙනවා.
I don't know, sir. He told like I started earlier and I just downloaded the earlier version.
Okay.
Like that.
Okay, that's a different story. But then again, you still get some Arduino controllers and these microcontrollers which runs on 32 bits. So for those for those controllers, you need the 32-bit version. You can, even if you compile using a 64-bit version, you might have to convert it back down because it might not exactly work. So you get that type of problem. So that's why you have the 32-bit. Okay, so here we can see how it how the 255 or the 128, sorry, the 8-bit binary system works. Okay, so now here, if you go down here, can you see this part? So an 8-bit computer game from 1980s to 1990s. So this is how it works. So that means each and every pixel and all these data points, they are the maximum they were able to consume was 8 bits. So these colors, sounds and everything, it was fixed into 256 colors. That was the maximum you could go forward. You think, okay, so when I got my PC with Windows 95 back when I was little, the color palette was 256 colors. We just got 8-bit colors. After that, after some time, when they released 16-bit colors, it was like really massive difference for us. So
then Excel was using Inkscape, sir. In those days, if you use Inkscape, sir, you would like say, tell to Inkscape what is this?
Yes, yeah. So those days, like the typical graphics were like this. This was the this was the typical type of graphics we had, even with the older games.
Even now
And
I understand, sir, why those very old movies look so weird.
yeah, because the color density is not there. So with 8 bits of colors, 8-bit colors, you can't do a lot.
Yes.
That's the whole idea. Okay, so then let's jump into the other point where we converting from binary to binary. Okay, so when it comes to conversion of this, we have two methods of doing this. Okay, so we have primarily we can take the divide by 2 method, where what we do is, since it's 2 to the power, so the base value is 2, so we just take the value, whatever the value which is there, and what do? We start dividing it. So when we start dividing it, so if we take the value 201, and when we start dividing it by 2, then what happens? The first step, we divide it by 2. Since it's 201, that means the remainder is 1, right? So 201, 201, දෙසිය එක දෙකෙන් බෙදුවාම 100ක් ඉතුරුයි. Sorry, the answer is 100, but you get 1 remainder. Then what happens? You get 100, you divide 100 by 2, 100 by 2, and the answer is 50, no remainder. Same thing goes down, we have 50, so we divide 50 by 2, 25, no remainder. Then we divide 25 by 2, and that is where the answer is 12. No? When you divide 25 by 2, the answer is 12.5.
We can't divide it, so sir, we get a remainder. We put
Yes, yeah. So we get 12.5 when you divide. So that means 1 remainder, right? Then 12 divided by 2, 6. That means no remainder. 6 divided by 2, 3. No. And 3 divided by 2, again you get 1. And 1 divided by 2, you get 0, right? So that means in this case, you can't divide it. So technically, with the remainder, you add 1. So that's how you get the calculation. So then what you do is, you start writing it not from top to bottom, but you start writing it from bottom to top. Okay, so that means when you divide 201, when you convert 201 binary to binary, the remainder would be, the binary represent would be this. Okay, so now if you want to convert it back again and try it out, then how it works? So you get the numbers, you get the place values, right? Now we have the place value table. So in this case, we can put the values in it. So this is like 8 bits, and then you just put the values and see. So we have 1 ones, no 2s, no 4s, 1 8, no 16s, no 32s, 164, and 128. So it all adds up to 201. Okay, so this is the most easiest method to convert the value. Okay, so let's see the second example. So let's convert 39 from binary to binary. So let's see how it works. It's the same structure we went through. So it's 39 divided by 2, 19. It's ideally 19.5. So we have 1 remainder. 19 divided by 2, 9. 1 remainder. 9 divided by 2, again 4.5. 1 remainder. 4 divided by 2, 0. That means no remainder. 2 divided by 2, that means 1. Again no remainder. And 1 divided by 2, again you have 1. Okay, so remember මං දැකලා තියෙන එකක්, most of you get this calculation wrong. When you divide 1 by 2, the answer is 0, but then the remainder is already there. So it's always should be 1. Okay,
Yes.
because when you divide 1 by 2, you get 0.5, no? So that means that goes out. 0.5, that 0.5 is taken as a remainder. Okay, so that is taken out. So likewise, if we add this into a table to check the place values, see here how it works. So we have 1 ones, 1 yeah, so 1 ones, 2 1 2, we have 1 4, and no 8s, no 16s, and we have 132, which then adds up to, rest of the ones are zeros, so then it adds up to 39. Okay, so that's how the calculation works. Okay, so shall we try out something?
Okay.
Shall we do a number conversion and see? So
Okay, sir.
let me write this down. Hold on.
So we did these calculations in grade 5, sir. When we started IT.
Seriously? Okay, that's good. No, perfect.
Sir,
Okay.
our school did something very unfair.
Uh-huh.
That means when we was in grade 1, they didn't do IT for us.
Okay.
And they started IT for us from grade 5.
Okay.
Now, sir, they started IT for grade 1 also.
No,
Yes, sir.
seriously. From
Yeah, sir.
from
So, sir,
grade
we are
1
like,
itself.
yeah, sir. So they are learning like the same thing as us.
Yeah, obviously, yes. They should be.
So, sir, it's so unfair.
Okay.
So, sir, they will be like high-tech guys when they are in grade school.
Yes, yeah. So don't say it's unfair. My generation, when until the time we did A levels, we didn't had even, sorry, until we finished O levels, we didn't had the internet in Sri Lanka. So you guys are lucky. You all have internet at least. Okay. So shall we try to divide this number and see? 49.
Okay, sir. Sir, it is into binary.
Yes, yeah. Can you convert 49 to binary?
49 divided by 2,
Yeah.
49 divided.
Right. Write it down. Write it down.
Okay, sir, I'll put it straight.
Situndi, can you write it down as well?
Okay, sir.
Yeah. So follow the same principle and see how it works. So what do you get? You first.
Still.
Yeah, writing. Okay. Go on.
Sir, is the answer 110001?
Correct. Exactly. Perfect. Good work. So let me put it there. So it's no. Let me put something else.
Sir, last time sir told about that Chrome Chrome store, sir.
Yeah.
And sir, I just went to the Chrome store and I added a theme.
Okay. Yes, you can do a lot of stuff in it.
I even added a theme with the solar one,
Ah.
and I even added the plugin that sir told that when it comes a YouTube video popping out that
Yes.
thing.
Yes.
Even I added that plugin.
Okay. That's good. That's great. See, you can find a lot of additions in it, additional stuff. Okay, so just to go through the 49, so how to convert 49 in binary. So we divide it by 2, 24, divide 24 by 2. Sorry, when we divide it by 2, we get 24 but 1 remainder. 24 divided by 2, 12, no remainders. Again, 12 divided by 2, 6, no remainders. 6 divided by 2, 3, again no remainders. But then when we divide 3 by 2, we get answer 1 and 1 remainder plus 1 divided by 2 is 1. So technically the answer goes as 1 1 0 0 1 1 1 0 0 1. Okay. So shall we do one more and then jump? Yeah, we'll just do another 2 more. Can you do this? I'll give you a bit of a hard number now. Let's do 189 to binary. 189.
Sir, we are not allowed to use the internet, right?
No, don't use the internet. you won't get to use the internet at school, no? So not during the exam. So no, don't. Okay, got the answer. What happened?
Sir, shall I say the answer?
Yeah, sure thing. Kevin, were you able to finish it as well? Still going. Okay, yes, please. Siddhamli, go on. Yes.
0, 1 1 1 1 0 1.
1 0 1 1 1 1 0 4 ones, right?
Yes, sir.
Perfect. Yes, 1 0 4 ones, and finally again 1. Sorry. Does it take time?
Sir, it's 1 0 1 0 1 0 0 1.
Correct. 1 0 1. Oh, 1 0 4 ones. Where did you make the mistake? It's 1 0 4 ones and 0 1. We did 189. See the calculation.
Sir, I have written the 94 as 8.
94 as 80.
84.
84. Ah, okay. Yeah, that's the okay. Okay. So I will show you guys a quick website, but don't do this. Like I mean, use this as reference, but don't do this. Don't use it to answer questions. Okay. So you have this website called QMath. So QMath, it will. I'll send this on the chat. This is a website which you can learn a lot as well. Yeah, I sent it on chat. So QMath this actually provides a lot of tools and applications where you can actually try out. See, this will give you binary conversions, as well as it has some videos where it will kind of teach you how to easily let's say convert numbers and see how the conversion works. As well as what I do is I normally use this as a method where you have this URL on top now. See, okay. So in the URL, if you change the value, now this is 189. So let's say 234. You change it. Cool. Let's try something. 160. See, if you search on 160, you get the values. So you can use this type of websites to kind of make it easy to understand how it works. Okay. So yeah, so that will actually make it much straightforward and easy. So you know you can see and understand the calculations much better. Okay. So super. So guys,
Sir,
yes, shoot.
sir, I just made something, sir. Sir, this is, sir, I made sort of a search engine, sir. Sir,
Okay.
I made it is like a model of my one, sir. I got the search code only from ChatGPT.
Okay.
But I did other customizations, that name and the searchings and the
Okay.
websites, and that was made by me, sir. And sir, I just put the things in the chat, sir. Sir, see, sir, that code, sir. Sir, go and type Python and HTML, sir. Sir can get the websites by that, sir. I just made sort of a search engine called Chemical.
You created a file. Okay.
Yes, sir. Only the search code was taken, other all was made by me.
Let me check.
In the
Sure.
chat.
Cool. Chemical. Okay, let's first of all take a look at your code. Okay, so you have HTML and you have a search. So
Sir, I just added those HTML. You can go the URL and those developers,
yes.
and in that URLs, I just put the URLs of those apps, sort of like
Nice.
that
Yeah.
HTML developing does and those things.
Yes.
And
You are on mute.
Python or HTML like that.
Yeah, that's nice. Hold on. Let me. Okay.
Here we go. Like that, sir.
Yeah.
And the other parts are like that.
What? Sorry.
And you can just like click on those websites and go.
Yeah, that's nice. That's nice.
Sir, but I just wanted to show it to sir.
No, that's nice. Okay. What about the JavaScript? Can you understand the JS code?
No, sir, I just
This
still
one.
don't know what is
Okay.
JavaScript. But
Okay.
sir, only that JavaScript, like you have like to put those tutorials and
Yes.
those things, no?
Yeah.
Only just have to copy that and put the tutorials in that. Have to do the other things.
No, no, this is great. This is great. So
So in the
learn.
DP education, I just learned both HTML and Python. Both.
Okay. No, learn about JavaScript also. JavaScript is actually quite a interesting thing to learn because 90% of the almost most of the applications runs on JavaScript. Even like WhatsApp, chat applications, Gmail, all email applications, almost like Skype and Facebook, everything runs on JavaScript. So this is a good foundation start from. So play around with this, and that's a highly paid salary as well. I mean, that's a highly paid job also.
In the future, we are going to develop our target is to make a AI sort of, it is an AI thing.
Yeah.
That's it. Even from the smallest keyword, the search should be understood. So
Yes.
sir, even a guy who know little bit English, what like if we like now if we search what car,
Yeah.
normally if we don't get what is the car, no?
Yeah.
My target is to like if we even write W and T and H and C and
Yes,
A
it should
and
come
R,
out. Correct. Correct.
it
Correct.
should come
Yes,
like
it should
that.
come out. Yes.
So it's
Okay, so guys, I will have to wrap up the class now. So because I do have another A-level class after this one, so we have to jump for that. So yes, so just go through the calculations we did. So please do practice it. Just try out multiple conversions because you really need to practice because you are going to get questions in the paper. Of course, you are going to get both conversions, both sides. So converting of binary to denary and denary to binary. I know it's easy, but may see now you made a silly mistake. So when you're writing it down, you really need to be 100% accurate because if you made one mistake, the whole binary code gets jumbled. So that will technically lose you marks. So okay, perfect. So I hope it was interesting, and let's catch back next week.
okay.
Okay.
Thank you, sir.
Super.
Have a nice day.
Yes, you too. Okay. See you.
Have a nice day, sir.
See you.
Have a
See
nice
you.
Thanks, sir.
See you. Good night.
Bye,
Bye.
sir.
Bye.
Thank you.